right, so we're going to look at internal forces here. This is kind of like intro to mechanics of materials. If you like this kind of stuff, you're going to go nuts in mechanics of materials. It's also kind of like method of sections. So if you like method of sections, you're good here too. So we can solve this kind of a problem. When you look at this as a static student, your first thought, hopefully, is to go, oh, I need to find my AX. I'm calling that A apparently. I need to find my AY, and I need to find my reaction moment, MA. Okay, and then we kind of go nuts. We're like, oh, okay, so the sum of the forces in the X direction is just AX, so that happens to be 0, and you feel super smart. And then you got the sum of the forces in the Y, so I've got -5 minus 3 plus, what is that thing called? AY is equal to 0, so I've got, oh yay, AY is equal to 8 pounds. Look how smart I am. And then we do the sum of the moments about A, which is going to be that moment that we don't know what it is, -5 times the 2 inches, -3 times the, I almost said 8, but this is 10 inches. That equals 0. And so we end up with the moment about A, that reaction moment is going to be equal to probably 40, and then it's inch pounds. Beautiful. Okay. So this is kind of like the first thing we do in statics is just kind of come up with these reaction forces and we're good to go. But what happens if we look inside what's going on here? Like what's actually going on inside the force? And to me, this is like honestly the most exciting part of statics because you're starting to get into mechanics of materials. And for some reason, this was just like always the most awesome part. So let's pretend that we're like 4 inches in. And let's look at this point B. So the question is, what's happening at point B? Okay, so there's a couple of ways to think about it, but I like this one the best. So if I've got B, it's kind of like method of sections. I'm going to cut here, and then I'm going to cut it on the other side. Okay, so this right here point is B. And if you really want to get into the discussion of, well, is it like on B or before B or after B or what's happening, that is like way beyond the scope of what we're doing. And it's really not necessary because honestly, these things are continuous. So those kinds of discussions are really just for the philosophers and hippies of the mechanical engineering world. But I'm going to go ahead and draw on the things that I know. So I've got 5 pounds here, and that's located at 2 inches. And I still have my AX, my AY, so I'm not going to draw AX because it's 0. The AY is 8 pounds. And the MA is the 40 inch pounds. Okay, now over here on the other side, I've got the 3 pounds. And so those are all the same external forces that I already had, right? Okay, so this is super important. I had 1, 2, 3, 4, 5 external forces. Whenever I break up a system, I should still have 1, 2, 3, 4. Oh, and then the 5 is the AX, that's 0. I should still have the 5 external forces. I scared myself. I'm going to put this here as a 0 now. So I should have the same number of external forces, but now what's going to happen is since we've broken some things up, things that used to be internal forces are now going to be external forces. Okay, so what you can think about is what was going on right here is that B was fixed. It was a fixed support on either side. So B was fixed to the beam, not pinned at the beam. Does that make sense? So I guess for my brain, what makes sense is to think of it as a fixed. And I know anytime I have fixed, I have lefty, righty, uppy, downy, and the momenty thing, the bendy thing. So, so that's it. So that means it's somewhere here. B was fixed to the other side. So it should have an uppy, downy. It should have a lefty, righty, and it should have a momenty thing. Okay. And then on the other side, anything that would have been internal needs to be the equal and opposite. So it would have an uppy downy, a lefty righty, and a bendy. Okay, and just to be sure you're down with this, these are opposite, and this bendy is the opposite of this bendy. Okay, so they're fixed, so it's got the left, right, up, down, and bend. Okay, now I should go ahead and label my extra dimensions here. What's 6 minus 4? 10. I mean 10 minus 4 is 6. Okay, now I drew my arrows a specific way because I'm using Hibbler. And Hibbler and, I mean, there you could either say that you always draw this arrow going down, Or you could always say you draw this arrow going up. And it just kind of depends on what book you're using. I don't know what the other books do. I know for sure that Hibbler always has, if you're going left to right, this arrow is always down. And then the normal is always out and the bendy is always that way. Okay, so I drew it the way that I'm going to draw it, but that's just, I don't know how to say it except for that everybody has their own conventions, and for the purposes of everything, I'm going to use these conventions. What is annoying, though, is whenever Hibbler gets to mechanics of materials, for some reason, they just flip this arrow, and they're like, clearly, this arrow is the other direction that it's ever been before. Or maybe they flip something else. They flip something weird, and it might be this. Okay, so anyway, this one down here, this is called your shear. We call it V, and it's called shear. Okay, this arrowy thing right there. Wish there was a better way to do that. This one is shear. This one here is your normal. We call it N. It's going to bother me, but oh well. And then this one here is called, we'll still call it like M at B, and it's just called the bending moment, I guess. So this one here is called the bending moment. Okay, in the book, and then so as you're going left to right, usually that's how we're drawing our beams. Beam diagrams are pretty much always drawn left to right. And so at least with this book that I'm using, the shear always points down, the normal always points out, and the bending moment always makes a smiley. So they say like concave up or something up, and I can never remember what that means. So I'll just say, oh, it smiles, and see how it smiles on this side too. Like if you kept this side solid and it went like this, then you'd have a beam that looked like a happy face or a creepy, weird something. I don't know what that would even be. But anyway, how shall I say this? It matters if you want to get the right answer on your homework. If you were dude on, like a desert island inventing statics for yourself, it wouldn't matter as long as this one was always the opposite of this one. It's just like when we're doing stuff in tables, it's better if we all use like the same conventions. Okay, so all that to say, what I could do is I would come in here and I would label, I would label this one. Okay, so this is the shear at B, this is the normal at B, and this is the moment, the bending moment at B. And similarly, this is also the bending moment at B, the normal at B, and the shear at B. So I could solve either half of this equation, or I could solve either half of this section. So I could either solve this dude over here, or I could solve this dude over here. Now just looking, my happy thoughts are over here because, I don't know, it just looks less busy. Another nice thing is if for some reason you didn't have these, look, I don't even care what my reaction moments are over here because they're not even in the picture. So I happen to have them, which was great. But if you're kind of in a hurry and solving these quickly, sometimes you can avoid even having to learn those at all. So this is the side that I'm going to do, is I'm going to do the right-hand side, and literally for no other reason except that I'm lazy and, I'm kind of a programmer, and good programmers are lazy, and that just kind of bleeds over into everything else that I do. Okay, so this is the side that I like. So what I'm going to do is I'm going to come in here. I'll say, okay, so the sum of the forces in the x direction, that's negative NB, so that's 0. So look, the normal force is 0. This is not a shock. Almost all these problems, the normal force is going to be 0. All right, sum of the forces in the, that's supposed to be a y, in the y direction, I've got negative 3 pounds that's given, and then up the shear, and then that's 0, so that means the shear is 3 pounds. And then the sum of the moments about B, all right, so I've got that negative NB, and then minus 3 times 6 is equal to 0. So NB is equal to negative 18, and what is this? Inch pounds, like that. Okay. Very, very straightforward, not frustrating at all. Okay. Now that said, let's go ahead and do the other side just so I can prove to you you're going to get the same answer. So let's pretend that you're a glutton for punishment. So sum of the forces in the x, 0 plus NB. So here NB was negative because it was pointing the other direction. Here it's positive because it's pointing the positive direction. Okay, so that's equal to 0. So that means NB is equal to 0, which is the same answer I got last time. Yay. Okay, sum of forces in the y. All right, I have 8 going up, I have 5 going down, and I have VB going down. And again, you've got the negative sign in front of the VB because it's pointing down. So VB is equal to 3 pounds, which is the same thing I got again. Okay, now let's do some of the moments about, I'm going to do the sum of the moments about, I'll just do the sum of the moments about A, just for funsies. Let's do the sum of the moments about A and see what happens. So I've got negative 5 times 2. I've got negative VB times 4. See, I'm really doing this the most annoying way possible. I have the positive 40, and I have the positive MB, and that needs to equal 0. Okay, I think I've got all of them. So I've got minus 10 minus 3 times 4 is 12, plus 40 equals negative MB. And what's 40? Oh gosh, science. 40 minus 10 is 30, and 30 minus 12 is 18. Yay! Okay, so MB is equal to negative 18 inch pounds, and hopefully that's the same thing I got over here. Yes! Yay! Okay, so you can get the same thing, and I didn't have to take the moment about A. I could have taken the moment about B, and that would have been fine too. So the point of the method of not the method of sections, but the point of doing the internal forces is just getting used to the fact that you can do things on both sides and you just kind of pick whatever makes the most sense. Now you can do these in 3D. I'll just kind of show you right quick rather than making a separate video. Okay, so say you've got a pipe in 3D and you've got it cut. If you've got the X, Y, and Z coordinate system here, you still have the force coming straight out. So in the Y, I guess. So in the Y is going to be your normal. So normal, except I can't spell because spelling is hard. Math is fine. Spelling is hard. So you have the normal. And then you also have the uppy downy here and the lefty righty here. So we're still going to draw those as shear. So you have the shear in the Z direction and the shear in the X direction. So shear, these are shear forces. Okay, then you've got around the, how shall I draw this? It makes sense. Around this direction, this is M in the Y. Now that is your torsional. So the twistiness. Twisty. So that's the twisty moment, torsional. And then you have around the X, and then you have around the Z, MZ, and MX. So MZ and MX, these are just your regular bending reaction moments again. So we don't see a lot of these because that ends up getting super duper complicated. I don't even think much in mechanics materials that you see this in 3D, and even when you do, you're rewriting it in 2D to make it, because you're analyzing each dimension kind of separately. So we don't really have, I guess the rules are you just follow the right-hand rules. So positive, 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 you draw them all in as positive, draw all the arrows in tension, but you can do this in 3D. It's just that you're going to have 6 unknowns every time you cut something, which makes sense because it's just like if you have a fixed pipe, you've got the left, right, X, Y, Z, and then bending around each section. So it's just a fixed, which means that you have 6 unknowns. So same thing in 3D, just a lot more work.